All right, everybody, welcome back to relative velocity, and we're going to be doing relative velocity in 2D. One thing I just want to say about relative velocity in 2D is this is going to be a great preparation for the next chapter of projectile motion. So just know that not understanding it is not a good idea. It's really important to know this so that you can do well for the next unit as well. Okay, so let's look at this. A plane travels with a velocity of 80 miles an hour north with respect to the air. Determine the velocity of the plane relative to the ground if it encounters wind at, let's first do A, 10 miles an hour north. So this guy over here is going 80 miles an hour, let's say without any wind. However, if there's wind pushing it and it's north, so at 10 miles an hour, how's that going to affect it? I think we can, we're pretty much doing the same thing at vector addition at this point. We're just doing 80 plus 10, and then we have the resultant vector as 90 miles an hour north. Okay, so I think that's relatively simple. Um, I think it gets a little bit more confusing later on, but let's see. Now we have 10 miles an hour south. So again, we're going to be looking at this one now, which is pushing it down 10. And, similar kind of thing. We have 80 going up, and then we have 10 going down. And then the resultant vector is going to look something like this, which is 70 miles an hour north. Okay. The wind is slowing it down a bit, but it's still going up. And then at this point, I think it gets a little bit more tricky. So let me erase this. So we have 10 miles an hour west. Okay, so we're going to be looking at this one over here, and it's going to be pushing it at 10 miles an hour. So similar to what we were doing before, we're just going to be drawing a little bit differently now. So what does it say? Velocity. Okay, so we're looking for the speed and the direction. Okay, so we have 80 going up, but then we have 10 pushing it to the west here. So our resultant vector is going to look something like this. And then we also find this angle. Okay, so anyway, to find the resultant vector, we can just find r squared, this is r, the hypotenuse, is equal to 80 squared plus 10 squared. So we can do square root of 80 squared plus 10 squared. And then let me put that in my calculator. Square root 80 squared plus 10 squared. And we get 80.62. Okay, so we get 80.62 miles an hour. But we also need to find this angle here. So let me do that. Tan inverse is equal to opposite, which is 10, divided by adjacent, which is 80. And then this is going to give us that theta. Tan theta, 10 divided by 80. And we get 7.13 degrees. But remember, the angle is starting from this 0 point right here. So if we know this part over here is 90, and then if that theta is 7.13, it's going to be 97.13. Okay. Okay, so we have the speed as 80.62 miles an hour, and then 97.13. Okay. Okay, so now we're going to do the same thing for the other one. It's going to be mostly the same, but slightly different. So this one, again, this plane is going 80 miles an hour, pretending that that's going with no wind. But then we have like a gust of wind pushing it. And this time this gust of wind is going to the east, but this is 60 miles an hour. So that's a lot. All right, so let's see how this works. So we have 80, and then we have a gust of wind going 60 like this. And you can draw it different ways, but you'll get the same answer, but you can draw it different ways. But this is how I'm drawing it. And then this resultant vector we know is equal to the square root of 80 squared plus 60 squared. So let me put that in my calculator. Oops. 80 squared plus 60 squared, square root, and we get 100. Yeah, it's a 3, 4, 5 triangle kind of. Okay, so we get 100 miles an hour. That's what we find is the speed. But now we need to find the angle here. So let's find that. I'm going to do inverse tan is equal to opposite, which is 60, divided by adjacent, TOA, A is the adjacent. And this is going to give us theta. And then we can find the theta. 60 divided by 80 is going to give us 36.87 degrees. But remember, that's not exactly the angle we want. Remember, this is the 0 angle. So we want to find out what the direction is going to give us. We want to find this angle right here. And we know that both of these combined is 90. So we can find what this angle is here by doing 90 minus 36.87. Let's see what we get. And we should get 53.13. Okay. So I hope that makes sense. It was pretty similar to what we were doing with the mathematical vectors. So, but just adding a little bit of more scenarios and how this is applied with physics. All right, moving on. A plane travels with a velocity of 100 miles an hour north with respect to the air. Wind is blowing on the plane. Airplane ranked from fastest to slowest for which outcome would allow for the plane to move the fastest if you were looking at the plane from the ground. Wind traveling at A, 10 miles an hour north, B, 10 miles an hour south, C, 10 miles an hour west, D, 10 miles an hour east. Okay. So we should know that the fastest that it's going to be going is if it's pushing in the direction that it's moving, especially if the amount it's getting pushed is the same. So A is going to be the fastest from fast to slow. So good, great. And then we should know that B is pushing against it. So that's going to be the slowest. C and D are pushing to the side of it, which is going to make it go faster, but not as fast as A. And so since it's exactly perpendicular, C and D would actually be the same. And then B would be the slowest. Okay. Okay, so let's look at this example now. Pretty similar to the last one, but maybe a little more tricky. A plane travels with a velocity of 100 miles an hour north with respect to the air. Wind is blowing on the airplane. Ranked from fastest to slowest, which outcome would allow for the plane to move the fastest? If you were looking at the plane from the ground, wind traveling at... So again, similar thing, but this time we have different values. Okay, so we have 10 miles an hour north. B is 40 miles an hour south. C is 70 miles an hour west, and D equals 10 miles an hour east. Okay, so I want you to think about which one's going to be making this plane go the fastest from the perspective of the ground. And you really should be decided between two things. The fastest one is either A or it's C. Okay? And you could do the math to figure out which one's going to be fastest. Maybe we should know that that this is just going to be 110. That's like pretty simple calculations. We have the 100 plus the 10, and we get 110. And maybe we don't know what this is, so maybe we could do a quick Pythagorean theorem. So I'm going to do square root of 100 squared plus 70 squared, and then you get like 122. Okay, so we can see that the fastest speed is actually C. So we see that fastest is C, and then it's going to be A, and then it's going to be D, and the last is going to be B because it's going against the motion of the plane. Okay. All right, moving on. The president's airplane, Air Force One, flies at 250 meters per second to the east with respect to the air. The air is moving at 35 meters per second to the north with respect to the ground. Find the velocity of Air Force One with respect to the ground. Okay, so it shouldn't be too hard at this point. So we have this plane going 250 meters per second. And then air is going to be pushing, or the wind is going to be pushing up it at 35 meters per second. And then we have what this resultant vector here with the angle. So at this point, we should be pretty comfortable with this. So I'm just going to pretty much go through this relatively fast. Relatively fast. You hear that? Okay. Let me put this into my calculator. 250 squared plus 35 squared, square root. And then we get 252.44 meters per second. That's the speed. And now let's find this angle. I'm going to use tangent to find the angle, TOA. So inverse of tan, opposite, which is 35, divided by adjacent, which is 250, is going to give us an angle. That angle there, let's see, inverse tan, 35 divided by 250. And we get 7.97 degrees. Okay. And luckily, this time, this angle here is from the 0 point. So it's from the 0 angle. So that's our answer right there. Our resultant vector and our velocity is 252.44 meters per second at 7.97 degrees. Okay. All right. Moving on. Okay, this is a pretty good example. Hopefully you're able to watch it. I can't watch it here for copyright reasons, but anyway, let's move on. A boat is moving across the river facing. We're going to be doing a lot of these boat problems, so it might get repetitive, but it's important to know because it's definitely going to come up, and it's really helpful, especially for the next unit. And I know at the beginning it's going to seem really tough, but anyway, just you are going to get better at it, and the more practice is going to give you a lot more confidence, even if it looks impossible at the beginning. A boat is moving across the river facing directly at the shore. There is a current that pushes the boat east. What speed of the current will push the boat the most downstream when it reaches the other side? The current going 0 meters per second, not moving. The current going 5 meters per second. Maybe I just abstractly draw it going 5 meters per second. The current going 10 meters per second, or everything would be the same. Okay. So first of all, you could think about it first, but let me draw this. Let me erase some of this. How you should be thinking about this is, first of all, option A here. If there is no current and it's going directly across, it would just reach directly across like this. If it's going 5 meters per second to the right, it's going to look something like going like this. It's going to go kind of somewhat off course like this. And then if it's 10 meters per second to the right, we should know it's going to be going the most downstream, and it's going to look something like this. Okay. So the answer is C. Okay. All right, moving on. A boat is wanted to cross the river and get directly across from where it started without being pushed downstream. If the current is moving to the right, in which general direction would the boat need to be pointed for this to be possible? Okay, so you're trying not, now this time you're not trying to go downstream. So you're trying to go directly across, Sorry, I know that's not a perfect line, but directly across like this. You do not want to go downstream at all. So which way would you have to point the boat? The answer is going to be B, and that should make sense because you have to go somewhat against the current in order to go directly across, because if you try to just go directly across, you're going to get pushed down the stream like the last problem. However, if you angle your boat like this, you have a chance of going directly across and moving to the other side. Okay, next question. A boat is wanting to get across a river as fast as possible, and it doesn't need to be directly across. The boat's motor only has one speed. In which general direction should the boat be pointed for the quickest outcome? Okay, so we can see, the current is getting pushed this way. So we're wondering, okay, if we want to get to the other side, it doesn't need to be directly across. It could be, I don't know, it could go this way. It could go this way. Which way would be fastest? Should we point the boat directly up in order to do this? Should we point the boat more towards the left, or should we point it more towards the right? I think we could probably X this out. We know if that we pointed the boat directly to the left, it's not really going to get to the other side. So we could cross that part out. I think most of us would be fine with that. But some of us might be thinking like, oh, if we go kind of with the current, maybe it'll get us faster. Or you might be thinking, oh, if we kind of go just directly across, then we'll be covering the shortest distance. So maybe that's what will get us faster. Or you might be thinking, oh, if we point it directly straight, that means most of the speed will be going up, and then it'll go in that direction. So anyway, you could pause it if you want to think about it more. But the answer is going to be A. And the reason why the answer is A is because, and this is important, this is going to have to do with a lot of the problems, is we're trying to get directly across. Okay, so I'm going to call this like the displacement in the y direction. okay? Or the distance in the y direction. So we're trying to get directly across. It doesn't matter if we end up here, directly across, or here. It doesn't matter where we end up. We're just trying to get across. So that means the option where the speed or the velocity is the most in the y direction is going to get us across in the y direction the fastest. So let's say for option C here, this is great, but this velocity, let's call it, I don't know, 10, some of it will be in the y direction and some of it will be in the x direction. I don't know, let's say like 8 and 3. It could be whatever it is. So, but there's only 8 in the y direction. However, if we put the boats directly up, 10 of them would be in the y direction and not just 8. So that's why we want the most amount of speed in the y direction, which will get us across in the y direction in the fastest amount of time, even though we're going to end up somewhere around here. Okay. I hope that makes sense. It might be a little confusing. I do have a video kind of showing how this all works. And since this is a video that I made, I guess I can show it. Okay. Okay, I hope that video made sense of how this all works. If it didn't, maybe watch it again or whatever. But anyway, that was me just swimming and stuff. Okay, let's move on. Okay, so these are a lot of the mathematical problems that we're going to do now. So we're doing 3 of these. They're very similar to each other, but I guess the reason I'm doing so many of them is to hopefully get you comfortable and understanding of how these problems are done. Like I said, the next unit is going to be very similar to this, so it's important to know how to do this. Okay, a boat is traveling across a river with the speed of 44 meters per second north. Okay, so it's going 4 meters per second north. When it encounters current, which is flowing to the east with a speed of 2 meters per second. Okay. If the river is 120 meters across, what is the boat's velocity with the current? Okay, so part A here shouldn't be too bad. We've been doing lots of things like this already. So the boat's trying to go 4 meters per second north, but there's a current that's pushing it to this way. And we're just trying to find with the current, how fast is it going? I'm going to call this R. And we're trying to find the velocity. So there we go. So R, as we know by now, 2 squared plus 4 squared. Just doing the Pythagorean theorem here. 20, square root of 20. And we get 4.47 meters per second. That's the speed. But let's find this angle here. So I'm going to use tan. Again, we could use other things, but I'm going to use tan. Opposite, which is 2. Adjacent, TOA, which is 4. And this is going to give us an angle. 2 divided by 4. 26.57. But remember, the direction we want is from this 0 degree angle here. So to find this angle, we're going to actually do 90 minus 26.7. And that's going to give us, so 4.47 at 63.3 degrees. Okay. All right, moving on. Part B, how long will it take to cross? Okay, so there's a few practical ways of doing this problem. However, I'm going to do it in what I believe is the simplest way, and I'm only going to show one method. If you want to do the other method, that's totally fine, and I encourage you finding your own ways of doing these problems. But the reason why I'm only going to show this one method, and it's not going to be the most intuitive method, is because it is what I believe the simplest, and it is what's going to help you, especially with the next chapter, the most. Okay, so how long will it take to get directly, not directly across? How long will it take to cross? So if you go like this, you know the current's going to push you, and you're going to go like this. Okay, but I want you to know something. There's two kind of things happening. We have two directions. This is in 2D. We have the y direction, and then we have the x direction. So there's two kind of directions happening. When there are two directions happening, we can kind of separate those two things into those two different directions. So, and this is going to be really important. So I'm going to separate everything into the x and y components. So how I'm going to do this is I'm going to say two things. This boat, when it gets across, not directly across, but when it gets across, in the y direction, I'm going to say the distance in the y direction it's going to travel when it gets directly across is 120 meters. I don't know how much it's going to be traveling in the x direction. That's not really like given to me. So I'm just going to put this dx, this distance in the x direction, as unknown. The next thing is the velocity in the y direction. I know when this boat is going through this river, that in the y direction, I'm going to call it the velocity in the y direction is going to be 4 meters per second, because that's how fast the boat's going to be moving in the y direction. I know in the x direction, oops, not dx, vx. I know in the x direction, the velocity in the x direction is going to be getting pushed to the right at 2 meters per second. The next thing is the time. So time is not directional. It's going to be both in the x and the y, so we can find this. So now what I'm going to do is how I'm going to find time is on this y side, I have two pieces of information. I have the distance and the velocity. I have the distance in the y direction and the velocity in the y direction. And now I can use that to find the time. So this is how I'm going to do it. I'm going to do velocity in the y is equal to this distance in the y divided by time. Since we're looking for time, I'm just going to arrange this. T is equal to distance in the y divided by velocity in the y. Time is equal to 120 divided by 4. Time is going to be equal to 30 seconds. Okay. So I want to say that I believe that is the simplest way to do it. It's important to know that we can break things up into x and y components. I'm going to show the way that most people would probably solve this problem if they didn't see me do it this way. But I'm not going to go through it because you would get the same answer. You probably know that the boat's going to be traveling, and let me erase this. The boat's going to be traveling with the current this way 4.47 meters per second. And then once we find that angle, we can find what this distance is, this hypotenuse distance is with this angle. Once you find what that distance is, and then you have that speed for that in that direction, that distance, then you can find time. You would get the same answer of 30 seconds. I do feel like it's more complicated. I do think it makes more sense, but it is more complicated. And I also feel like the way I did it will help you more. So I'm just not going to show that way because I feel like I'm going to confuse people. Okay, let's move on to part C. So part C says, how far downstream do you end up? So this is dx. We're looking for what is the distance in the x direction that this boat goes. So again, I'm going to copy down what we know in the x and y direction. We don't know the distance in the x. That's what we're looking for. We know the distance in the y is 120 meters. We know that the velocity in the y is 4 meters per second. We know that the velocity in the x is going to be 2 meters per second. And we just found time. So we actually know that the time it's going to take that this boat's going to be in the water is 30 seconds. So we can actually use these pieces of information to find that distance in the x. Remember, time is the only thing that's the same on both sides. And we can only use the information on the side when we're looking for something. So when I'm looking for a distance in the x, I shouldn't be using velocity in the y. I should be using velocity in the x. So let's use that to solve for this. So let's see. Velocity in the y is equal to this. Oh no, so velocity in the x is equal to distance in the x over time. And if we're just looking for distance in the x, we should know distance in the x is equal to velocity in the x times time. Okay, so let's figure out what that is. Velocity in the x is 2 times time, which is 30. So we should know that distance in the x is equal to 60 meters. All right, I hope that made sense. Try to do the next one on your own. It's very similar. We're going to do 2 more of these that are all very similar, and see if you can try to do it on your own. And if you can't, then anyway, just follow what I'm doing. But I'm going to do the next 2 quicker. All right, so let's look at this example 41. A motorboat traveling 4 meters per second east encounters a current traveling 3 meters per second north. I'm not sure why this says current over here. Okay. What is the velocity of a motorboat relevant to the Earth? Okay, so pretty similar. I'm going to go through this one a lot quicker than the last one. Just because last one I took a long time, and I'm hoping that, well, one, I'm hoping you pause it and you're doing this on your own first, but 2, I've already talked about this, so look at the last one if you're having more of an explanation. So the motorboat is going 4 meters per second east. The current is taking it 3 meters per second north, and we're trying to find what the combined velocity is. And I'm not even going to do the Pythagorean theorem. I know that this is a 3, 4, 5 triangle, so I know this is 5 meters per second. So that's how fast the boat's going to go with the current. I am going to find this angle. I'm going to use tan. Opposite is 3, TOA. Adjacent is 4. And this is going to give me an angle of tan inverse 3 divided by 4 of 36.87 degrees. And luckily, since this boat is going to be moving like something like this, we don't know, this angle here, it's already kind of showing starting from that 0 point. So we already know that's going to be 36.87 degrees. So that's our answer right there. 5 meters per second at 36.87 degrees. Okay, part B. If the width of the river is 80 meters wide, how much time does it take the boat to travel from shore to shore? Like I said, multiple ways of doing this problem. I'm going to be showing what I feel like is the simplest way and the way that's going to help you the most, especially with the next unit. Okay, so we're dividing everything we know in the x and in the y direction. So I know that the distance in the x direction, if it's going 80 meters wide, so this is 80 meters in the x direction. We know that this boat is going to travel some distance in the y direction. I'm going to call it dy, but we don't know what that is currently, so I'm just going to put question mark. We know that this boat is in the x direction going to be going 4 meters per second. We know in the y direction, it's going to be going 3 meters per second thanks to the current. We don't know how long it's going to take to get to the other side or travel these distances, but we know it's going to be the same on both. So time doesn't have a direction, so it'll be the same for both. So I am looking for the time it takes. Luckily, on the x side of things, we have 2 pieces of information here, and that can help us to find time. Okay. On the y, we only have 1 piece of information, so that's not going to be too much help as of now. Okay, so velocity in the x equals distance in the x divided by time. And then I could do time is equal, manipulate this a little bit, distance in the x divided by vx. So time is equal to distance in the x, which is 80, vx, which is 4. So this is going to give me 20 seconds. Okay. What's important to know is it's going to take 20 seconds to get all the way across, and it's going to go in this diagonal motion, but it's going to take 20 seconds to get all the way across. But what we should also know is this is for both in the x and the y direction. So as it's moving in the x direction and in the y direction, and it gets to the other side, it's going to take 20 seconds. Okay, 20 seconds. Okay, part C is how far does the boat travel downstream before reaching the shore? Okay, so that is what it's asking for, is this distance in the y direction. That's how far downstream it's going to go when it reaches the other side. Luckily, we already have two pieces of information in the y direction now. We have the velocity in the y direction and the time. So now we can find this distance in the y direction. So velocity in the y equals distance in the y divided by time. We're looking for distance in the y. So we could just do velocity in the y times time. Velocity in the y is given to us. That is 3 times the time, which is 20. So this is going to be equal to 60 meters. All right, hope that makes sense. We're going to do one more problem that's very similar to this one. Hopefully, this next problem you can do completely on your own. But again, we want lots of practice for the next unit and because this is a little bit difficult. All right, guys, let's do the last example for this chapter, for this unit. Again, I'm going to go through this one quickly. If you want a more thorough explanation doing problems like this, please look at example number 40. But here we go. A boat is traveling across a river with a speed of 5 meters per second north. Okay, 5 meters per second. And actually, you know what? I'm even going to put that on the other side. Okay, 5 meters per second. When it encounters current, which is flowing east with a speed of 5 meters per second. Okay, so this current is also pushing it 5 meters per second. If the river is 100 meters across, what is the boat's velocity with the current? Did many of these, so again, I'm going to go through this quickly. We have 5 meters per second, and then 5 meters per second. And then this resultant vector here is going to give us, what's it going to give us? It's going to give us the combined value, how fast it's going from the ground, perspective from the ground. Okay, let's go to 50. And we get 7.07 meters per second. Great, that's the speed. And now we need the direction. So one thing I'm just going to say right away is, yes, usually you need to do math to find the direction. However, one thing I know is this is 5 on one side and 5 on the other side, meaning they have the same side. So this is going to be 45 degrees right here, which means since this whole thing is 90 from this side, that means the side also is 45 degrees. Okay, but anyway, we could do the math just to see. So tan inverse opposite is 5 divided by adjacent, which is 5. And this is going to give us an angle. I'll put in my calculator just to satisfy everybody. 45 degrees. Okay. And so, yeah, that's what we get. 7.07 meters per second at 45 degrees. Okay, how long will it take to cross? Again, I'm going to be doing the x and y components. I'm going to be seeing what I know in the x and what I know in the y. I'm going to use that to figure this out. So distance in the x direction, we don't know. This boat's going to be traveling something like this when it gets to the other side. We don't know how much it's going to be traveling in the x direction when it gets to the other side. So that's a question mark. However, we do know that it's going to travel 100 meters in the y direction to get to the other side. We do know that the velocity in the x direction as it's traveling is going to be 5 meters per second thanks to the current. And velocity in the y direction is going to be 5 meters per second thanks to the engine in the boat. We don't know the time, but we do know it's the same on both sides because time doesn't have direction. So now we can use this to figure out time, how long will it take to cross. I'm going to use the information the y because we have more information on the y side. Velocity in the y is equal to distance in the y divided by time. So I'm going to use time is equal to distance in the y divided by velocity in the y. Distance in the y is 100, velocity in the y is 5. So that means time is equal to 20 seconds. It's going to take 20 seconds to get directly, not directly. It's going to take 20 seconds to get across. Okay, what we should know, again, time doesn't have direction. So what we should know is time is going to be the same for both sides, for both the x and the y. So 20 seconds and 20 seconds. When we're doing part C here, it says how far downstream do you end up? So what that's looking for is this distance in the x direction. We're looking for that. We don't know what that is. However, now that we know time, we have information to find what this distance in the x direction is. Velocity in the x is equal to distance in the x divided by time. We want to find this distance in the x. So put this t on the other side. Velocity in the x times time is equal to distance in the x. Velocity in the x is 5 times time, which is 20. And we get distance in the x is 100 meters. Okay. And yeah, it's going to be the same as this. And that should make sense. It's going the same speed in the x, in the x and the y. And it's traveling with the same time of 20 seconds in both directions. So the distance it goes should be the same in both the x and the y. All right, thanks for watching. Thanks for watching this whole chapter. I hope that I see you in the next chapter. Bye.